Hello, everyone. Welcome back. Today, I'm going to do something that I didn't quite wanted to do, but I think it's going to be necessary. I'm going to give mainly results without proofs. There will be references, and there is a whole class dedicated to this topic. I hope that the abundance of examples and things will help making this go down a little bit easier. But I don't want to spend more time on this stuff because that's not the main topic of the class. So let me quickly remind you where we arrived on Thursday. So we have C, a simplicial set. We decided to call it is an infinity category if for every n greater or equal than 2 and for every I between I and n and for every map f0 from the inner horn into C. And remember, this was the union for all j different than I of the j face of delta n inside delta n. For every such map, there exists f from delta n into C extending f0. And the intuition, let's see, I'll give more intuition in a second, but the case n equals 2, sorry, I equals 1, this is saying every pair of composable arrows can be extended to a full 2 simplex. Encoding the composition. We can compose arrows. And okay, let me give a bunch of examples. First, so let C be a category, an ordinary category. Then n of C is an infinity category. In fact, these I'm pretty sure is going to end up in the exercise sheet. That should be very easy. And bolstered by this example, actually, we will often call the 0 simplices of C objects and the 1 simplices arrows, as I've already started doing. Another example is let X be a Kan complex. Then X is an infinity category. Okay, this is almost tautological. The definition of Kan complex is basically the same without this restriction on I. This restriction of I. You would allow I in 0 and n. And today we will see exactly what kind of infinity categories are Kan complexes. So you can think of the objects of this Kan complex as points of your space, and the arrows are as paths. And well, more generally, if C is a Kan-enriched category, its simplicial nerve is an infinity category. This was the motivating example, if you want. A category where we have a notion of object of homotopies, we can actually repackage in this infinity category. And let's see. Do I have other examples I want to give? No, not really. And another thing, for today, I'm going to put this nerve in front of 1 categories to denote that I'm getting an infinity category. But I will see in a moment there is a canonical identification of categories inside quasi-categories, inside infinity categories. And so starting from the next class, I'm going to silently drop this and just identify the category with the associated infinity category. Because it just simplifies the notation and it's helpful. Okay. Oh, actually, let me record, so we will call 0 simplices of C objects and 1 simplices arrows. Okay, just to get it written down. Other questions?
For infinity categories, can we require the horn filling condition also for n greater or equal to 3 and I equals 0 and n?
No.
Okay.
No. And in fact, well, I think this will be clear in a minute, but when you think about it, by applying to the generate horns, you see that if you have it for big N, you are very close to having it for small n's. And you actually, the easiest way to think about it is to see what happens for a one category, for the nerve of a one category, and see that this is really not something you can ask.
Thanks.
Okay, so let me first state a characterization that might or might not make this definition go down easier, which is very similar to the characterization we gave for Kahn complexes using the homotopy lifting condition, homotopy extension condition. I'm not going to prove it. If you remember, that proof was sort of technical. This is basically the same idea, but longer. I'm going to put a reference in the notes. You can read it at your leisure. You can even try to do it on your own, because really the idea is basically the same. Okay, so let C be a simplicial set. The following are equivalent. 1, C is an infinity category. 2, for every diagram of the form, today. There exists a lift. And then the 3 is similar. I'll explain the intuition behind it in a second. Just let me get it written down. There exists a lift. So actually, yeah. So what's the intuition behind this? So you should think of these as this hum from lambda to 1 to C as simplicial set of pairs of composable arrows, because that's what the zero simplices are, right? Zero simplices are pairs of composable arrows like this, and higher simplices are just, families of these, for example. One simplices are things like this. So delta 1, if you want maps between such diagrams. And this is simplicial set of pairs of composable arrows with a choice of composition. Oof, I can spell. Can you read this color I'm using, by the way? Yeah, okay. Because sometimes there is a difference between how Zoom portrays the colors and how my tablet does. And sometimes I use a color that it's beautiful here, but the audience cannot see it. So I'm just asking to be sure. Okay, so that's the intuition. So this map, essentially, you have a pair of composable arrows with a choice of composition, and you forget about, so here, X, Y, Z, this. Maybe not directed, just feel like this. And you forget the composition, And this is telling you essentially that the space of such compositions is contractible, which is, you can actually think of it as in two statements. First, it's non-empty. So you can actually find such a composition. That's the n equals 0 case here. For any pair of composable arrows downstairs, you can find in one upstairs. But then it's also telling you, for example, for n equals 1, it's telling you that each two pairs of composition can be connected by a path, for example. Each two choices of composition are homotopic, as we will see in a second when I define what homotopic means. And bigger n is just telling you more and more stuff. It's homotopy means they're path connected, bigger n it means they're higher and higher connected until you end up with saying that there is just a contractible possible choices of composition. So if you want a simplicial set as an infinity category only if composition of arrows is well defined up to a contractible choice. That's the intuition behind this lemma. Okay, questions about the statement? The proof, I'm really not going to say anything more than it's similar to the other one, where you could actually just choose extend homotopies. Here you extend choices of composition. It's just the same strategy, only with bigger simplicity, so it's harder to draw, but it's not really. And as a corollary, remember, we got a corollary out of this statement in the case of Kan complexes, and the corollary here is also useful. So if you have C an infinity category and S a simplicial set, then hom SC is an infinity category, which we write fun SC, and we call it the functor category. And maps of simplicial sets between infinity categories will often be called functors. And you can think of these as the infinity category of diagrams. In fact, we will spend most of today thinking of these as the infinity category of S-index diagrams. Now, we defined it only in the case where S is the nerve over one category, but of course, nothing changes here. And okay, how do you prove this corollary? Well, we apply our nice criterion. We have a fun lambda to 1. Oh, sorry, hom. I haven't proven yet, so I'm supposed to keep using hom. B, and you want to find that there exists a lift. Right, that's characterization C, or 3, what's the 3. But use the adjunction, and you see that this is the same thing as finding a lift here. And that exists because C is an infinity category. Okay. So this is verbatim the same proof that we did for Kan complexes. So that shouldn't be a surprise, but it's very useful. And we call this the functor category, or let me also say the category of diagrams. Infinity category of diagrams. So again, for today, I'm still going to try and be a good boy and say infinity categories every time I mean an infinity category, but I will drop the infinity at some point because the goal of today is to give you examples and show that infinity categories behave pretty much the same as categories. There are a couple of important differences, but even those are essentially telling you that they behave better even. So there's nothing you should be afraid of. And I'm just going to say a bunch of definitions and statements that you should know from ordinary category theory and try to give you some intuition about why they are still true. Okay. Good. Okay, but I promised you mapping spaces at some point. Mapping spaces are kind of a tricky thing because there are several inequivalent definitions. I know at least 4 of them. I'm not going to give you all of them. In fact, I'm going to give you only one of them, but very often to prove a property, you have to prove that 2 models are equivalent and go to the other one. Because mapping spaces are not going to be defined on the nodes. As I say, there are going to be different Can complexes that are all homotopy equivalences in a canonical way. And I've made a choice of one of them, which has the disadvantage that it's slightly trickier to prove it's a Can complex, which is what I'm not going to do. But it will make me easier to define the composition. So just in the interest of brevity, I'm going to present you only with this model. Just to show you. So, okay. Definition. So let C be an infinity category. And now let X, Y objects of C. I'm going to define the mapping space as well. You take the functor category of all arrows. So these maps to C times C by taking source and target. And here you can take just the 0 simplex corresponding to X and Y. This lies. Let me write it down. Lies. So this fun delta 1 C to C times C comes from precomposition with delta 0 inside of boundary delta 1, so delta 1. So we take the source and the target of the arrow. Okay, and fact, which is slightly fiddly to prove. I spent most of yesterday actually trying to find a neat proof of this, but in the end I decided that I'm just going to assert it. It is true, and I'm going to put a reference, but the proof is fiddlier than I wanted to present today. Let's see, X comma Y is a Can complex. Okay, my tablet is having problems. 1 second. Okay, good. You can see it again, right? Yes, perfect. I don't know what happened. Okay. Okay, but does this definition of mapping space make sense, modulo the fact that you actually have to prove that it's a Can complex? It's not the most natural one, actually, but it's the one for which composition is most easily defined. So I'm going to go with it. And okay, then let's define composition. And the trick is, well, we can take map C X comma Y times map C Y comma Z. So this is just the product. And this is just, if you look at it, it's just a collection of all composable arrows lying above X, Y, Z. If you look, these are literally the same simplicial set. Okay, canonically identified as simplicial sets. Again, same is a bit in the eye of the beholder, but come on. You see what I mean? And we want to get a map to map C x, comma, z. But this is going to be hard. But what we have, remember, we have this map from fun delta 2c times c, 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 x, y, z. Forgetting. And okay, I can put the empty set here if I want to have exactly the same diagram as before. And actually I probably should have written upside down. But the point is I can choose a lift here. And now these maps to fun delta 1 c times c x comma z by taking only the second phase. Actually, let me shrink this so I have more space. Just by taking the one phase. Okay, there were problems hearing. Should I repeat something?
It's fine.
It's fine, okay. Sorry, my tablet had some problems. I don't know. I hope the connection doesn't do anything funny today. Okay, but anyway, this is just map cx comma z. And actually you can play with these properties and see that this map is in fact unique up to homotopy, in fact unique up to a contractible space of choices, etc., etc. The space of all such maps fitting in this nice diagram is just contractible. So we have actually a well-defined, you don't have a single composition map, but you have a contractible space of composition maps. And the slogan is that's good enough for what you want to do. Again, we lose a little bit compared to the model of Cannon-Rich categories, but we gain something. Oh, and I didn't say what the identity is, but the identity arrow is, okay, yeah, let me say, actually. The identity arrow is a lot easier. It's just SX in fun delta 1C. It's just the degenerate one. The degenerate one simplex at X. And you can actually check composition with the identities, homotopy to the identity, and etc., etc., etc. Everything is fine. Again, I'm not going to give many details today, but hopefully it's clear that everything can be made rigorous. Okay. Yes.
I have a short question. Can you quickly elaborate a little bit on why this lift exists?
Okay, so let me write it better. So where were from delta 2c times sorry, I'm writing a bigger diagram, so maybe it's going to be clearer. That's going to take me a second. No. Okay, so what is this? Actually, this again. Okay, this is just a classical identification, and these are just the inclusions of the fibers. These are the inclusions of the fibers into these things. In particular, this is a Cartesian square. And this is just the inclusion of the empty set. And actually, if I wanted to choose one that's compatible with the identity, I could actually put the inclusion of the point. That's the identity here, if I wanted to be fancier, but I'm not going to. So, okay, we have this big square now, this big square here. that is exactly the square as in the lemma. You have an inclusion on the left-hand side of simplicial sets, and the right-hand side you have that projection. So you know that you can find such a lift here. And then since it's a pullback square, you can find the lift here, as promised.
Okay, thank you.
Okay, good. And again, as I said, here you could actually put the degenerate guy and get a composition that's compatible with the identity on the nose. But, sorry, not the degenerate guy. Let me say, okay, but that's only when, I don't know, x is equal to y or y is equal to z, otherwise it wouldn't make any sense, of course. But, okay. You can put like, not the degenerate guy, actually, I mean the subcomplex of degenerate guys. That's not what I mean. Okay, you know what? You can put a fun delta 1c, but let me not make it precise because I'm going to get lost in the details and that's really not important. Okay. And actually, let me put a fact. That's actually easy enough that I might give it as an exercise, but I haven't decided yet. So 2 arrows f, g, x to y are connected by a path in map c x comma y if and only if they are homotopic relative to the boundary in the old sense, i.e. there exists a 2-simplex f g, the identity of y. So this is not, they're not literally the same data. A path in this mapping space I've written is different from an homotopy in this sense, but you can actually prove that the space of these two gadgets are the same. And it's fairly easy to see because a homotopy here instead is f id x id y. It's a square like this. It's a path here. And the 2-simplex, as I defined earlier, is a 2-simplex like this. Homotopy, like I defined it earlier, is a 2-simplex like this, but it's, if C is an infinity category, you can fairly quickly show that these two, given these two amounts of data, are the same, again, up to a contractible chance. Let's see if I can make it doable as an exercise. I want to see what kind of precise statement I can extract. And moreover, let me put this other fact. You can say H is homotopic to G composed with F for some choice of composition if and only if there exists a 2-simplex like this. It's clear that if G is homotopic, a 2-simplex needs to exist because G is obtained factoring these two simplices. That in fact you can show that if such a 2-simplex exists, you can find a composition functor that sends G composed to F with H. So I didn't lie when I said the notion of composition. And actually, let me put another fact about mapping spaces and then I'll move on. Map n delta c x comma y is equivalent to map, sorry, n delta c underline x comma y for every can-enriched category. C underline. So the two notions of mapping spaces are not literally the same. You can see that this guy is bigger, but it's bigger in ways that don't matter. A simplex here is a more complicated diagram in C underline than just an arrow, but it's contractible. There is a canonical map in this direction, I think, that is an equivalence. Okay. Let me pause for 1 second. Okay. No questions? Everyone is on board with these mapping spaces and all this fun stuff? Okay. Then let's see. Let's define. Actually, I can put a line. So let C be an infinity category. Then the homotopy category is the ordinary, or one category, whose objects are the zero simplices of C, and such that I didn't put it a name. Give it an HC. 0y is pi 0 map C xy, or equivalently the homotopy equivalence classes of morphisms x to y, and composition is given by applying pi naught to any of the composition maps. Which one you choose doesn't matter, because it is they're all homotopic, so the map induced on pi naught is the same. And actually, I haven't even said it, but you have to check that these composition maps are associative up to homotopy and etc. in order for these to actually give you a category. But again, this is just playing with simplices. It's not a hugely complicated proof. And let me give you an example. So let space be this simplicial nerve. We call the infinity category of spaces. Then its homotopy category is the homotopy category of spaces that you have studied in the last couple of semesters, I think. So objects are spaces equivalent to a CW complex, and maps are homotopy classes of maps. Well, okay, that's not the definition. It's equivalent to this one, but by the discussion we did. And that's a very important object. That's the first step you can use. You can also do the infinity category of pointed spaces by taking pointed Kan complexes, for example. And so on and so forth. And that's because by the fact I said before that in a Kan-rich category, the mapping space is literally the mapping space in its nerve. It's literally the mapping space. This is just saying you take arrows in these Kan-rich categories and you take equivalence classes of arrows, like path component of your map, x, y. Okay.
I have maybe a short question. How hard is it to define the category of spaces without going through Kan-rich categories?
So I don't know of any definition. I can give you universal properties that will characterize that uniquely, but you have to prove that such an object exists. It's not enough to give a universal property. I don't know of, I mean, you can take, of course, n delta of CW complexes. That would also work. Or you can play funny games. There are other Kan-rich categories you can build that will have an equivalent nerve. There is one using posets, for example, that's kind of fun. When you think the poset as like telling you how to glue things, but in the end, you are... Okay, now there is a way of doing it without Kan-rich categories, using using the theory of localizations. You can show, well, I haven't defined equivalences yet. You can show the space is, for example, you take Kan as a one category, or CW complexes as a one category, and you invert the arrows in the infinity categorical sense, which I will define in a second, and you get space again. I don't know if this is more or less satisfying, but that's another thing.
Thanks.
At some point, the point is that the reason why I'm doing all this is at some point you need some kind of concrete input. You can try to axiomatize, and it actually I think it's very valuable to give an axiomatic description of what you want to work with. But to prove that such a thing exists, in the end, you need to construct it. It's not something new. And also, you would like to know that this is related to topological spaces in the classical sense sometimes, which is where I spent so much time in the first couple of lectures to give a motivation for why these things. Okay. Okay, but since I was talking about equivalences, let me actually define what an equivalence is. So let's see. C infinity category, f from x to y arrow in C. Is an equivalence if its class in HC is an isomorphism. Or equivalently, if there exists G from Y to X, such that GF is homotopic to the identity of X, and FG is homotopic to the identity on Y. This shouldn't be a particularly scary definition, but it turns out that there is this hugely fun fact that now I defined you only giving like an arrow and two equivalences, but F is equivalence if and only if the map delta 1 into C that picks out F can be extended to the nerve of the contractible groupoid of two objects. So this is a groupoid with two objects, 4 arrows, and the compositions are fixed by whatever you want. And note that this gives a G and an infinite amount of coherences because you have all the higher simplices of this nerve that give you bigger and bigger homotopies. So the fact that such a G, such that GF and FG are homotopic to identity exists, tells you automatically that you can build an infinite amount of coherences. And another fact that's actually used in the proof of the above fact, but it's slightly less intuitive, so let me say it later. F is an equivalence if and only if for every alpha from lambda and 0 to C, such that, I always get this wrong. Yeah, alpha restricted to 0, 1 is F. There exists alpha bar to delta n to C extension. And let me just draw the case n equals 2 so that we see what we're doing. So here you have alpha is this kind of diagram. Then you can find alpha bar, which you want to think of something like that. And the proof of these two facts is not very long and complicated, but I'm skipping it in the interest of time. Because I would need to define what a left vibration is, and I don't want to do that now. But I'm going to put a reference, it's actually kind of pleasant. Okay, as a corollary of this fact, C infinity category is a Kan complex if and only if all arrows are equivalences. And actually, I said this statement with lambda and 0. You can actually do the same fact for lambda and n. Of course, it's just symmetric. Yeah, but it turns out that lambda and 0 is enough. That's why Kan complexes are sometimes called infinity groupoids, because they're just infinity categories with all the arrows are equivalences. I don't particularly like this terminology because it's, I tend to prefer to just call them spaces because it's shorter, but it might bring confusion. So there are a bunch of names. Okay, oh, I forgot an important example actually. X Kan complex, you can ask what is the homotopy category of X? And we know it's going to be a groupoid. And let's see if anyone has a guess about what groupoid this thing is. At least people that were in algebraic topology 2 last semester. You should have a good guess.
Oh, I think if X is thing of space, then it should be the fundamental groupoid.
And it is. And in fact, if you can do the definition of fundamental groupoid for a Kan complex, you can check it goes down verbatim. And it's indeed what the definition of a homotopy category is. So, okay. Sorry, I forgot, but this is an important example that I think it's useful to keep in mind. Okay. Okay. Well, we're going perhaps a bit fast, so let me ask if you have questions about this so far. No. Okay. Then let me draw another line, and now we finally go towards the definition of limits and colimits, which was the original reason why I want to do all this rigmarole. And let's start with the most stupid possible example of limits and colimits. So let's see, be an infinity category, X and C object. Oh, okay, let me say ob-C. One second, at some point I will stop writing ob. When I say that something is an element of C and C is a category, hopefully no one has any doubts about what that means. So let's say that X is initial if for every Y object of C, map Cx, Y is contractible. Remember, the definition in one category land is initial if the home set is a singleton. Now we just have a homotopy type, so we say, well, it's contractible. The maps from X to Y there is only one map up to a contractible choice. Or if you want, there is a contractible space of maps. Similarly, X is terminal if for every Y of C, map C, Y, X is contractible. Okay. Well, this definition shouldn't be particularly compelling, but okay, let's say X. So C is the nerve of the one category, ordinary category. X in ob C is initial if and only if it is initial in D. And similarly for terminal, because then the mapping space is literally the discrete. Oh, I didn't remark it, but okay, when you look at the definition, the mapping space is literally the discrete set of home in D. So a discrete set can be contractible if and only if it's a singleton. Okay, and X complex has an initial object if and only if it is contractible. That also shouldn't be a surprise. Groupoids normally do not have initial objects. Unless they're a trivial groupoid. Okay, so now I'm going to give you the definition of limits and colimits, but I wonder if I should repeat what the definition of limit and colimits is in one categories, or if people are comfortable with it. No, you're comfortable with it? Okay, let's see. I'm going to give you a definition that works verbatim for one categories. Hopefully it won't be too different from the one you've seen. So, okay, well, I'm going to allow a little bit more flexibility and let S be a simplicial set. And let me define the left cone. Oh, maybe it's the right cone. Oh, maybe that's the right cone. Okay, I'm going to get to left and right probably wrong at some point, but okay, it's the simplicial set such descending n to pairs f, sigma, where f is a map from, well, let's say delta n to delta 1, and sigma is a map from f inverse of 0 into S. So how should I think of this? Well, let me give you an example, and then maybe I'll draw some pictures. If S is the nerve of a category, then S, cone is the nerve of this category cone, where C cone has objects, the objects of C plus another object I'm going to call infinity, and hom C cone xy is going to be hom C xy if xy are both in C, in an object of C, sorry. A point if x is in, well, if y is infinity, both if x is an object of y or y is infinity, and empty if x is infinity but y is different from infinity. So you should think of it, I have my C here, my diagram with whatever arrows it has, and I'm adding an object infinity such that everything has a unique map to it. If you take C opposite, I'm just adding an artificial bigger object bigger than all the other objects in my poset. And there is also the left cone, of course. So in general, so if S is some simplicial set here, I don't know, something like this, I'm adding an object, infinity, and I'm gluing a face for each face in S, one dimension higher with infinity as the biggest. That's the delta one. So an n-simplex in this S cone lies over delta one, and I have to specify its starting phase, which is some if you want, I have to specify a 1 in an I in 0 n, and then a map delta 0 y into S, and the rest is forced by the cone. Right. This might be a bit weird the first time you see it, so please tell me if there are problems with it. Okay. I'm going to give you, oh yeah, let me give you another example that's going to be important. Let S be lambda to 0, which is, I'm going to think of this poset here. Then S cone is just delta 1 times delta 1. Yeah, actually this I'm going to give it as an exercise. Yeah, I think it's a good exercise to just see what's happening. Okay. Questions about this notion of left cone? No. Okay. And now, so okay, let's C be an infinity category. And P from S to C a diagram, by which I just mean any map of simplicial sets, where S is any simplicial set. So for our purposes, it will be 95% of the time a nerve of a poset, but we give the general definition. A colimit of P, and then sometimes people put homotopy, but it's to remind us that we're in homotopy theory, I think it's not very relevant at this level of generality of P, is a diagram P bar from the right cone into C, such that P bar restricted to S is P, and it is an initial object of the category of such diagrams, which is, I'm going to write as fun S colon C times fun SC. That's category of such diagrams. This is, I don't know, when I was back in undergrad and I opened MacLean categories for working mathematician, this was literally the definition of colimit that is in that old book. I don't know how it relates to the definition of colimit you've seen in your studies before, because there are various ways of defining colimits. But and also in infinity category length, there are various ways of defining colimit. I'm just choosing this one because I think it's the closest to the classical one, and it's and okay, I'm not going to say it, but for example, if you take S a discrete set, then the colimit is called a coproduct. And if you take S, this lambda to 0 that I wrote before, it's going to be called a push-out or homotopy push-out, and etc. And okay, I'm going to put as an exercise, so it's a bit hard when S is lambda to 0 and C is space, this notion of colimit coincides with the notion of homotopy push-out we have seen last semester. Because giving such a cone is exactly a square, we discussed it, is exactly a coherent square in the way we discussed it, and the fact that it's initial is exactly telling you that the map from the standard homotopy push-out we wrote is an equivalence. Or to be precise, that maps out of the homotopy push-outs can be written as this. I give a map, another map, and a homotopy. And that's, you have to unwrap a little bit what all these definitions do, but that's exactly what it's telling you, because this square now has the information of this homotopy. Okay. Remark, there's a dually defined notion of left cone and of homotopy limit, of limit. Okay. Good. So the rest of today is going to be spent by giving you examples of homotopy limits and colimits, and giving a very important property of homotopy colimits in spaces. That's called the scent property or Van Kampen property, which is going to be essential when we're going to do the reconstruction theorem. And that's it. That's how we're going to spend the last half an hour. And this is going to be the end of the background section of this class. But other questions before I go further?
What is the conceptual way to see functors out of a general simplicial set to an infinity category? Is there sort of a free infinity category construction that,
Yes.
that we should imagine in between, or?
Yes, for example, let me give you a silly example. S, let's take lambda 2, 1. That's a simplicial set, which is not an infinity category. And when you think of fun SC, you can think of it as equal, actually it's equivalent Oh, I should define also what an equivalence of infinity categories is at some point, probably. But okay, this is equivalent to the same functors from delta to C. So in this case, the free infinity category generated by S essentially gives you also a composition. It's just delta 2.
Thanks.
And there's always a way of doing it, but I mean, it might be a bit inexplicit in general, of course. Imagine it's like a special case of this is the free category generated by a graph, if you think about it. Now that you can actually still work with, even if it's a bit inexplicit. Or you can do something fancier and take the free category generated graphs where you mark some arrows as equivalences, which means like adding some other arrow and some, you can imagine like gluing an arrow going in the opposite direction and homotopies of the two compositions, and do it in a free manner. This is just a simplicial set. You can just write it down, and this provides you, well, you can actually write any infinity category that way, with a graph and some arrow marked as equivalences. So can be quite inexplicit, but you can do that. Okay, actually, okay. Before I go on with these, actually, since I was reminded that I didn't define what equivalences of infinity categories are, let me fix this problem and define directly the infinity category of infinity categories. So actually, okay, let me give you a bunch of definitions. So let's see the infinity categories and F, G from C to D functors. Natural transformation F, G is just a point in in map fun CD from F to G that we saw being an infinity category before. So this makes perfect sense, and you can unwrap in the case when CD are one categories and CDs is just the normal notion of natural transformation. If you remember, normal notion of natural transformation is just giving a bunch of arrows for each object and some commutative squares. And if you unwrap what this mapping thing is doing, is exactly doing that. And okay, so the space of natural transformations is map from CD F G. And okay, okay, but that's not quite the definition I wanted to give, sorry. I wanted to give the mapping space in infinity categories. And this is the full subcategory, by which I mean the simplicial set, the biggest simplicial set containing the vertices I'm going to describe, the full subcategory of fun CD, spanned by the equivalences, by okay. Okay, I'm doing this. So sorry, full, okay. No, not spanned by the equivalences, sorry. Maximal Kant subcomplex of fun CD. Okay, sorry, I was getting this wrong. By which I mean you take all objects, all arrows that are equivalences, and then all higher simplices whose one simplices are equivalences. And that's why I wanted to define the space of natural transformations, or what a natural transformation is. And then cat infinity is just a delta of Q cat, where Q cat is the simplicial category. Sorry, the simplicial category whose objects are infinity categories and map qcat cd is what I defined, map cd. So functors and natural equivalences.
Maybe just a remark. I guess this maximal kind complex we can pretty easily write down using the homotopy category as a pullback.
Yes, 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 yes. Let me put a remark. Let me write the remark. That's a good remark. So if C is an infinity category, its maximal Kan subcomplex is just C. Well, I promise I will write the nerves here, where this tilde here denotes just the maximal subgroupoid. So it's actually a rather concrete object. And sometimes it's written also iota C. I actually tend to prefer it's called the interior, but or sometimes it's called the moduli space of objects. But anyway, okay. Okay, so an equivalence of infinity categories is just an equivalence in cat infinity. So remark equivalence f c to the of infinity categories is just equivalence in cat infinity, i.e. there exists G from D to C such that G is isomorph of G, F is isomorphic to the identity of C, and F, G are fixed to the identity of D. As you would presumably expect from the one category. And that's the fun fact that when you take one categories and you define the one categories, there is a definite difference between the notion of equivalence of categories and the notion of isomorphism in the one category of categories. But here there isn't. Here we can talk about the infinity categories and it just works. We don't have to be worried about that. That's one of the first of the many ways in which infinity categories are actually better behaved than normal categories. You don't have to introduce a new notion of equivalence. The old one will work just as well. Okay, sorry, I even wrote it in my notes that I should talk about these and then I forgot, but thankfully someone reminded me.
Excuse me, I didn't get what in the example HC equivalence sign means.
Oh, this is just the subcategory of HC with all objects and all equivalences. All isomorphism, sorry.
Okay, thank you.
Because it's a one category. So it's a subcategory, so. Okay. Okay, questions? Okay. If there are no questions, I'll go back with examples of limits and colimits. And in fact, I want to do. So, okay, I just need one more definition. No. See, infinity category, a zero object, zero in ob C is just an object that is both initial and terminal. You've probably seen this before for one categories. Yeah. So, okay. So let me give you definition. So C, oh, and C is, if C has a zero object, it's called pointed. This is our terminology that we import directly from one category land without any modification. So let me give you an example. So C pointed infinity category, for example, pointed spaces, which is where the name is coming from. You take, well, there are various ways of defining, but one way to define it is just take the simplicial nerve of pointed Kan complexes and base point preserving maps, but there is also an intrinsic way from the category of spaces to define it. I don't want to give all the details now because I don't want to talk about slice categories yet. The suspension sigma x of x in C is the homotopy push, is the push out. X goes to 0, goes to 0, goes to sigma x. And you probably, if you've been in last semester algebraic topology 2 class, this definition is quite natural if you believe in that statement. That the homotopy push-outs and pullbacks that we discussed last semester are the same thing. The same thing that, as before, the loop space omega x is the pullback. Okay. Okay, and my claim is that these sit into an adjunction. Okay, I haven't defined what an adjunction is for infinity categories, but it's the same thing as for one categories. And if you remember, the loop suspension adjunction was quite important last semester, and it's going to be even more important in this one. We will upgrade it to an equivalence in a special case. But in order to do that, I need to have it. So let me fine. So let me show an example. So let's say, what is maps from sigma x into y? Well, this is a homotopy push out. So this is the same thing as maps in the functor category from this diagram into y, into the constant diagram. That's another way of writing that initiality property of the colimit. I am kind of hoping that you've seen this before for one categories, because I could do everything, but we will have to spend the whole semester doing these things properly for infinity categories. And here it really works the same. And so if you unwrap everything, this gives you the same thing as maps in C from X to Y. Actually, let me write it like this, putting this in the center. Map in C X to Y, maps in C 0 to Y, and the same thing. No, let's go to a new line, because otherwise it's going to be cramped. It's not going to help anyone. And that's a point here. What I'm saying is that it's the same as giving a map like this, a map like this, and a map like this in a way that they glue together. these pullbacks are these naturality squares I was discussing earlier. But if you look at this, this is the same thing as maps in lambda to 0, sorry, lambda to 2, see? And now we have the constant diagram here and this guy here. And so that's the same thing as maps in C from X to omega Y. These are actually, I'm writing equality, sorry, but these should really be equivalences. They're not the same simplicial sets. They're homotopy equivalent. And so sigma omega are functors with a natural equivalence like this. And we say such a pair is an adjunction. And we write sigma adjunct omega. Again, if you've seen these in one category landed, this shouldn't be too surprising. And of course, there are like at least 5 other equivalent ways of specifying an adjunction, giving unit and co-unit, triangular identities, and so on and so forth. Again, I could spend a whole class proving all the equivalent ways, but I'm not going. Again, I'm going to refer to other things. Okay, this is very important because these guys, this is the adjunction we're going to make an equivalence to get spectra from pointed spaces. Spectra, in some sense, is the universal way, universal category where this is an equivalence built out of pointed spaces. But we will discuss this on Thursday, or maybe this particular thing on next Monday. Okay, questions about this?
Yes, I have a short question. In the second line, this is the one categorical limit, no?
No. This is always, sorry,
Okay.
I should have mentioned.
So we also take here the higher categorical one.
Yeah.
Okay. So this encodes automatically the right homotopies.
Yes, exactly. Yeah, okay, let's say that from now on, and all the limits I'm going to write down are going to be homotopy limits, and all the co-limits, homotopy co-limits. And that sometimes people put a little h to remind you of that, but it gets, since we're going to have a lot of them, it gets quite clumsy after a while. So okay, let me give you another example, which is the so-called geometric realizations. And I'm going to give you the Gauss-Filkan formula. So a geometric realization is just a colimit of a diagram X from delta up into C. But the reason why I'm doing this is because in a very special case, I have an explicit formula for geometric realizations. And I'm going to do it when I have actual topological spaces, but you can do the same thing with simplicial sets. But I'm doing it for explicit topological spaces just for the sake of concreteness. So let X from delta up to top be a simplicial space. And here I really mean a simplicial space. Then we can consider X bar, composition of this guy, top to space, to n delta, well, okay, n of top, delta can, that is spaces.
Excuse me. Do you now mean again one categories, ordinary categories and ordinary co-limits?
No, I mean here, I mean a homotopy colimit. Well, a colimit in whichever sense whatever the target is. So a normal colimit when C is a one category, and a homotopy colimit when C is an infinity category.
Okay.
But here, when I write top, I mean actually a one category. Otherwise, I would write spaces. I'm
Okay.
being careful about that. But this, if you have a functor into top, you can get a functor into spaces by taking this and sing here. You can post-compose. And you can ask what the colimit of this x bar is. And the colimit of x bar is, and just let me put a sing here just to remember that I'm going to give a topological space, but it's actually thing. It's taken by the same formula as before. Only now the product is in spaces, modulo the same equivalence relation here. So for every f n to m, how was it? F upper star little x t is equivalent to x f lower star little t. As points in, well, okay, this lives in x m delta m, and this lives in x m delta m. That's the equivalence relation we wrote last time. And okay, why am I doing this? Well, first of all, because it's a fairly explicit type of homotopy colimit I can actually write down. But also because you can build all homotopy colimits out of coproducts and geometric realizations. So having a formula for the geometric realization is going to be useful. So let me say theorem, the Bausfeld-Kahn formula, which was actually Bausfeld and Kahn original definition of homotopy colimit in their yellow book. Although you probably wouldn't recognize the formula I'm about to write down from the formula that I wrote, but it is the same. So let x I, no, s, sorry, I called it s to C a diagram. Then there's an equivalence between the colimit of x, and there is also a similar one for the limit, actually, but I'm just going to write down the colimit, and the geometric realization of the simplicial object n goes to, and that's disjoint union over all n simplices of S of x of sigma of, I hope it's n. It's either n or 0. I always get it wrong and I didn't prepare here, but no, I think for the colimit it's probably n. So where this is just the last vertex of sigma. This is an element of S0, so X sends it into an object of C. And the simplicial maps are pretty much the only one you can write down in this context. That's, if I write it down, there is just this cases. It's not very enlightening, but if you try to write down a map, there is the only one. It's essentially the only one you can write down. So there is this formula, so you can know, if you know how to compute coproducts, which are typically easy, and geometric realizations, you won. And just to give you an example of this, if you have a push-out diagram, the push-out is given diagram. So let's say this is T. T is equivalent to the geometric realization Oh, and now I realize, no, that has to be 0. Otherwise, the formula I'm about to write is false. Sorry. It's n for the limit and 0 for the colimit, and I always mix them up. Mathematization of n goes to y disjoint union x disjoint union x n times disjoint union z. And you might recall in one categories, T would be given by the co-equalizer of this thing. And this is sort of the souped up version of that for infinity categories where we add higher coherencies to deal with the homotopical limits. Because the first piece in infinity categories, our simplicial diagram is of the form. So that's n equals 0, you just get this thing. N equals 1, you get this thing. And the two maps are exactly those two maps. And then you have also the silly one that just inserts an and then, but then you have to add higher coherencies like this. And then let me just write another 1, 3, 4, etc. So when you take the colimit in a one category, it's enough to take the colimit of this piece by some cofinality argument in one category land. But when you go to infinity category, it's not enough anymore, and you have to take out the full simplicial diagram. And actually, unwrapping what this means and seeing what the pushout does is fun. I mean, it helps getting an intuition for what is going on here. For example, the pieces coming from here give you 3 simplices that telling you that the two maps from, so part here gives you a homotopy that the two maps from y and z to t are homotopic when restricted to x. But then when you pull it back, there are 3 possible ways you can glue these homotopies, and this isn't telling you, oh wait, they are, these 3 possible ways are actually the same, and you go on and go forth, and this tells you higher information. Okay, I think I'm going to state descent when I'm going to use it actually, instead of stating it now, because I think we're out of time, and this is going to be, I think, in 3 or 4 weeks. I just wanted to say it earlier for the sake of having it written down, but I don't think it's worth it doing it like super quickly now. I'm just going to state a special property of colimits in spaces. Okay, so I think I want to stop here.
I have a short question regarding the last example. When C is an infinity category, then what do you mean by diagram simplex category up to C?
Oh, sorry, yeah. I lied that I wouldn't, that this time I would remember to put the nerves everywhere. This time I forgot. I actually mean the nerve.
Okay.
From the nerve. But from next week, I'm actually not going to put the nerves. When I'm going to have a map from a one category to a simplicial set, or from a simplicial set to a one category, actually means silently inserting a nerve.
Okay, okay. Cool.
And actually, for the sake of this, actually, let me give you an exercise, and this is pretty sure it's going to be in the exercise sheet. The nerve of fund CD is the same. It's actually the same simplicial set in this case as these two things. When CD are categories. So I'm not really lying too much when I omit the nerves here. Other questions? Oh.
I have sort of a tangential question. In the last exercise sheet, we had in the last question an action of the fundamental groupoid on the higher homotopy groups. By last semester, in nice cases, we can associate to this thing a covering space. Is there anything interesting one can say about this covering space?
Not any more than what we did last semester. I mean, you can redo the theory of last semester and it just works. You need a notion of covering space for simplicial sets, of course, but you can do it. But in some sense, it's less interesting because when you move to Kahn complexes, you are essentially forcing everything to be homotopic. While the power of the theory of covering spaces was that covering space is inherently a geometric notion, and you turn it into a homotopic notion, moving from one to the other. And if you work only with Kahn complexes, you actually don't have that. So that's also the reason why covering spaces are typically done with topological spaces, because it's very useful. I mean, of course, this action is secretly controlling the universal the action on the universal covering space, right? You have an action on the universal covering space, and the homotopy groups are the same, and so this action of pi1 is secretly seeing the action of pi1 on the homotopy groups of the universal covering space. But of course, this is nothing more than what we did last semester.
Thanks.
Other questions?
I just wanted to say that for me, this lecture was again too fast.
Yeah, I'm sorry. Okay, I'm going to slow down from next time. Now I have all the definitions in place, and next time, actually next Thursday, the only goal is to prove the Brown representability theorem. It's only one theorem. It's going to be one statement. Hopefully, it's going to be more reasonable as a piece. I'm sorry. I just wanted to get all the technical stuff away before we start doing what we want to do. Maybe I should have allocated another lecture to the background because it was a bit too much. But, okay.
Excuse me, it might be a dumb question because we just took like 3 or 4 lectures to introduce an infinity categories, but how much of that infinity stuff is
is needed,
is required to understand the stable homotopy course? Because
I mean,
fast for me.
You're not going to have to remember all the details, but I'm going to define the infinity category of spectra because spectra really don't have a nice one categorical model like spaces do. There are one categorical models you can work with, but they're very awkward, and especially when we're going to introduce multiplicative structures, they're going to work very badly. It was a famous open problem until the late 90s that you couldn't construct one category of spectra that behaves multiplicatively in a nice way. There is an impossibility theorem due to Lewis. So I'm going to use this terminology because of these advantages. But if you are a bit confused by the notion, don't worry. I think actually using it in practice is going to clarify it a lot more than just giving you a barrage of definitions. But for example, I'm going to say, oh, a spectrum is a sequence of spaces together with an equivalence of one of them with a loop space of the previous one. And that's, I mean, it's as big, this formally it is this pullback in cat infinity, which if I just said it, you might have felt a bit cheated, perhaps. That's why I wanted to give you the actual definition of things. But it's not really required to understand the intuition behind it, if this makes sense.
All right, thank you.
Okay. Okay, I'm going to stop the recording and see you Thursday.